Hello student friends. Today we are going to start with Unit 5, which is State Variable System Modeling. To give an outline, in this video we are going to cover introduction, some important definitions, and state space model for single input and single output LTI system, and some problems based on that. Coming to the course outcome of this unit, in this unit we are going to construct state variable models for electrical and mechanical systems and inspect the concepts like controllability and observability for system performance analysis. In this particular video, we are going to cover a state variable model for electrical system. The further part of this unit will be covered later. Now, the current control system theory that we are going to study or that we are studying is called classical control theory. As you know that all these days whatever we have studied, we have always considered single input single output systems. So classical control theory is basically suitable for SISO systems like LTI systems, and the system is represented by transfer function. So far whatever we have studied, the different concepts all included that the system was always represented by a transfer function, right? And the classical control theory is difficult to apply for multiple input multiple output systems. So only we have a modern control theory which is suitable for MIMO system, that is multiple input multiple output systems. Unit 5 is kind of introduction to the modern control theory. This is particularly suitable for non-linear systems as well. And in this case, like in classical control theory, we represent a system by transfer function. In modern control theory, the system is represented by state variables and state equations. Now, what are the advantages of using the state space techniques? As I already said, it is suitable for MIMO systems, and we can easily analyze the time domain behavior of the non-linear systems. And modern control theory is compatible with simulation on both analog and digital computational environment, and we can also analyze the stability of a system where we do not have a unity feedback system. For example, in most of the cases whatever we have studied so far, we consider unity feedback system. That means feedback is same as the output. So in some systems where the feedback is not same as the output signal, it becomes difficult to analyze the stability. But by applying state variable technique or state space technique, we can easily analyze the stability of the system. And there are cases that there are some applications where Laplace transform cannot be applied. Classical control theory is basically useful when the system is represented by transfer function. Transfer function is nothing but it is in S domain, that is Laplace domain. Suppose we have a system which cannot be expressed in Laplace domain, then we have to use state space technique. And one more important and very useful advantage here is all the equations in state space technique are first order. So it is like it is very easy to analyze because all are first order systems. Like in classical control theory we had higher order systems as well, but in this case all are first order systems. Now coming to the definition, I'll just read out the definitions. The first one is state space representation. It is a mathematical model of a physical system represented by a set of input, output and state variables related by first order differential equations in case of analog systems, or first order difference equations in case of discrete systems. This means the system is completely represented by inputs, outputs and state variables. So the word state variables is very important here. So to understand it better, I'll give you an example. Before that, let us see how the state variables are defined. It is a smallest set of linearly independent system variables. I repeat, it is the smallest set of linearly independent system variables such that the values of the variables at time t equal to 0 along with the inputs forcing function at time t greater than or equal to 0 will completely determine the behavior of the system. Okay, to give a generic example, consider our system is an object. We have an object, and my system or the output of my system is to find the position of that object at any given point of time. Okay, I repeat, I have a object as my system, and my task or output of my system is nothing but any point of time what is the position of the system is the output of my system. Now consider that I know the initial position of the object, and the object is at rest. I have an object and it is at rest and I know its position. Suppose you ask me what is the position of the object at any given point of time, so I can easily say that. Suppose initial position of my object is, let me take sorry okay, suppose I have an object and its initial position is x. If you ask me at any point of time t, what is the, suppose I take it as x naught, what is the position of this object at any point of time, then and I know that the object is at rest. So that means I can say that initial position itself, that is x naught itself, is its position at any point of time. That means its initial position will act as a state variable. That means I'm able to find its output at any point of time. Now suppose the object is moving on a with a uniform speed. It is moving in one dimensional direction with a uniform speed, or I can say uniform velocity. Suppose I want to know the object of the position of the object at any point of time, then what are the things that I need to know? I need to know its initial position and also a speed or the velocity with which it is moving. So output of my system can be determined only when I know these two parameters, that is x naught and v. So these two parameters or these two variables will act as my state variables to give an output of this system at any given point of time, t greater than or equal to t naught. Now assume that it is not moving in a uniform speed. What happens? It is varying. So then I also need to know the acceleration to understand or to determine its position at any given point of time. So in this case I need to know x naught, which is initial position, velocity and acceleration, to find the position of the object at any given point of time. So these three parameters will act as my state variables. Now is that clear? State variable, what are the minimum number of variables that you need to know to understand the output or to determine the output of the system, or it need not be only output, any parameters or any variables of the system. With just the knowledge of system variables, or sorry, state variables, with just the knowledge of state variables, I can determine the values of all the system variables at the time t greater than or equal to t naught. Now the next definition is state vector, which is all the system or the state variables together will form a state vector. It is simple. Next, state space is, it is an n-dimensional space whose axes are state variables. If you define a space with axis being defined by these state variables which we had decided, then that entire n-dimensional space, suppose there are n state variables, the n-dimensional space is called state space. Now as in the example we had seen that depending on the condition of the object, whether it was at rest or moving in a uniform direction, or it was moving with uniform direction, uniform speed, and with a uniform speed or not increasing speed or accelerating speed, we decided how many number of state variables we need. So the selection of state variables becomes very important when designing a state space model for a system. So in general, we can say that the number of state variables is equal to the order of the system. So take an example that a system is a first order system. Then the number of state variables is nothing but the number of, that is first order system, so it is 1. For a second order system, there should be at least 2 state variables. Now to take a general example, we have to follow. So here are some guidelines that we can use for selection of state variables. So in case of discrete time systems, the output of delay elements, unit delay elements, will act as state variables. It is kind of guideline or hints for you. In case we have a continuous time system, the outputs of integrators will act as state variables. In case of physical systems, output of energy storing elements will act as state variables. For example, mass and damper, M and B, will act as state variables. In case of electrical system, the outputs of energy storing elements, again here in case of electrical system, the inductor and the capacitor will act as the energy storing elements, but not the resistor. Now let us define a state space model for a single input single output LTI system. The state model is a combination of, or the state equation and output equation together is called state model. Now what is state equation? State equation is an equation expressed as x dot is equal to ax plus bu, where here are the definitions. X is nothing but the state vector. As I told, state vector is nothing but the vector formed by state variables, and x dot is the differentiation of this state vector. So nothing but x dot is dx by dt, and a and b, here they are defined. A is called system matrix and b is called input matrix. Now there is another equation which is y is equal to cx plus du, where c is output matrix and d is feed forward matrix, and y is nothing but the output vector, and u is input vector. So for now you need to just remember that state equation is always x dot is equal to ax plus bu, where you have, so a, b, c and d are all the matrices, and what you need to remember is x is a state variable vector, y is the output, u is the input. A, B, C, D are all the matrices. These are the different names given to those matrices. Now this is types of state equations. Simple. If it is x is equal to, if it is x dot is equal to ax plus bu, where I have this u quantity, that is input quantity, then it is called non-homogeneous state equation, that is u is not equal to 0. And homogeneous state equation is nothing but when it is input is 0, that means there is no input given, x dot is equal to just ax, is called homogeneous state equation. Now in this unit we are going to cover both homogeneous and non-homogeneous state equations. Now let us solve some simple problems based on this. So as a first problem, I have taken a very simple electrical network, the RLC network, where R, L and C are in series. And the question says to obtain the state model for this. Now the first thing to identify here is what is input, what is output. In the circuit diagram itself, it is given that V0 is the output, which is the voltage across the capacitor, and Vi of t is the input. Now we need to identify what are the state variables. Now, if we go back to the guidelines which we went through, here in the last step, the last point, it is given that in an electrical system, outputs of energy storing elements are nothing but the state variables. Now, what are the energy storing elements? L and C, that is inductor and capacitor. In our example, the energy storing elements are L and C. There are two energy storing elements, therefore, there are two state variables, and we can say this is second order system. So, two energy storing elements L and C, therefore, two state variables. Now, one more hint here is whenever you have L, that is, whenever you have inductor, I take a current passing through that inductor as my state variable, and whenever I have a capacitor, I take voltage across the capacitor as my state variable. So, one simple hint, for C it is voltage and for L it is current. Now, in the same way, here the state variables are chosen. So, I of t is the current passing through the inductor, therefore I of t is one state variable, and the voltage across the capacitor, I take Vc as the voltage across this capacitor, and that acts as my state variable, that is Vc. Now, what is x dot? X dot is nothing but the differentiation of x, therefore for I of t it is dit by dt, and for Vc of t it is dVc of t by dt. Now the next step is to obtain the system equations in terms of state variables. Now I need to obtain my state equation and output equation. What is state equation? State equation is x dot is equal to ax plus bu. Right, what is x dot? X dot here is di of t by dt and dvc of t by dt, and I need to, now my job is to obtain the equation for di of t by dt and dvc of t by dt equal to something, and those equations should be in terms of state variables which are nothing but I of t and vc of t, and also it is x dot is equal to ax plus bu, that means it can be in terms of input as well. Now how can I obtain that? For analyzing an electrical network, I have different options. I can go for KVL, I can go for KCL, or I can go for any other theorems as well. Now the simplest ones to use are KVL and KCL. So in this case, as I have a single loop, I can apply KVL to this. So here is the KVL equation where it is Vi of t is equal to Ri of t plus L di of t by dt plus Vc of t. It is simple and straightforward. Now here I given one more hint that for while writing the voltage across the capacitor, I could also write, or the usual way of writing is 1 by c integration of I of t dt. But I suggest whenever you are writing state equations or whenever you are writing electrical equations, as far as possible avoid integration terms. It is easy for you for getting the state equations. So the voltage across capacitor, that we have already decided, the voltage across capacitor we have taken as Vc of t. So instead of writing 1 by c integration of I of t, which is nothing but the voltage across the capacitor, Vc of t, you can write it straight away. Now what I need to understand, now I need to get the equation for di of t by dt. Therefore I can move this term on the other side. So I move this L di by dt, keep it here, and move the remaining terms on the other side. You will get this equation. I need di of t by dt, so move L to the RHS. So I get minus R by L. This is the last equation, which is for di of t by dt, which is the first element in the x dot matrix. Next, now I need to write one more equation. I need to write one more equation in terms of again state variables. So how do we decide whether to apply KVL or KCL? It all comes by practice. When you solve more and more problems, you will understand how to get the equations. Here in this case, I'll write an equation for Vc. Vc is nothing but the voltage across the capacitor, that I can write it as 1 by c integration of I of t dt. But what I need x dot, where the second element is dvc by dt. So differentiate on both the sides. So I'll get 1 by c, integration and differentiation get cancelled. So I get I of t. Now what I got in the previous case was, so basically I wanted di of t by dt and dvc of t by dt. By applying KVL, we got di of t by dt. And another equation, which is now voltage across the capacitor, we got an expression for dvc by dt. So I'm rewriting both the equations again. Now write these two equations together in a matrix form. So that should be in terms of x dot equal to ax plus bu. On LHS you already have ax dot terms, and on RHS, so you should write the coefficients. So here you can see x is nothing but, so you know what is x dot, you know what is x. Now what is A? A is nothing but the coefficient matrix. So here you can see how you can write this matrix. So I need to, in the first equation, and this is first equation, what is the coefficient of I of t? That is minus r by L. Coefficient of Vc of t, that is minus 1 by L. In the second equation, what is the coefficient of I of t? Is 1 by c, and coefficient of Vc of t, there is nothing, so it is 0. Okay, plus it should be b into u. What is u? U is the input. Input is nothing but Vi of t. In the first equation, what is the coefficient of Vi of t? 1 by L. In the second equation, what is the coefficient of Vi of t? There is no Vi of t term, so there it is 0. Now this is the state equation in where it is of the form x dot is equal to ax plus bu. And you can correlate the matrices here. This is matrix A and this is matrix B. Now we got the state equation. Next step is to get the output equation. Now write the output equation. What is output? Output is nothing but V naught of t, which is the voltage across the capacitor, which is Vc of t. This is very simple, but I need to write it in the form of y is equal to cx plus du. How can I write this? I can write V naught as 0 into I of t. I should write it in terms of state variables and the inputs. Here I could also add, here I need to write the equation in terms of state variables, that is I of t and Vc of t. I can also write it as 0 into Vi of t as well. So my equation should be in terms of state variable plus the input variables. Now I can write it as, can rewrite this in a matrix form like this. So write the coefficient of I of t as 0, the coefficient of Vc of t is 1, and the coefficient of, here as I said, 0 into Vi of t, the coefficient of Vi of t is 0. So this takes the form of cx plus du, where you have this 0 and 1 as matrix C and D is just 0. Now here we got the output equation. Now your state equation is this and the output equation is this. They both together will form a state model. Now let us go to the next problem. So I have named it as problem 3 because it is the same problem which is there in your notes, which is already shared with you. Now observe this. So this is a multiple input example where you have one input as a voltage input as Vs and another current source as Is. And they have also given you the values of inductor, capacitor and resistor, that is 1 Henry, 1 Farad and 4 ohm respectively. Now what is the first step? First step is to identify the state variables. Again, identify the energy storing elements. Here there are two energy storing elements, L and C, one inductor and one capacitor. As I told you, for inductor we take current through that, and for capacitor we take voltage across that as the state variable. The same thing is shown here as well. Now I name the current through the inductor as IL, and I name the capacitor voltage across the capacitor as V0. It is up to you how do you name it. So in the previous case what we did, we named it as V0 also and we named it as Vc as well. In this case the question says output is the voltage across the capacitor. Inputs are clearly seen, Vs and Is, and they're told consider the output as the voltage across the capacitor. So the voltage across the capacitor I named it as V0 and that acts as Vc as well. So it is up to you. So in this case I have solved it in a different way. Instead of naming two variables, that Vc also V0 also, Vc or V0, V0 itself will act as my state variable. The current through inductor IL and voltage across capacitor V0 will act as my state variables. So what is the x dot? It is the differentiation of whatever we have state variables, dIL of t by dt and dV0 of t by dt. And one more thing to note here is there are two inputs, therefore my U matrix, there are two inputs in this, Vs and Is. Now next step is to write the equations. So as a first step I apply KVL to this loop. So as you are well aware of loop equations, I hope you understand the equations clearly. The input is Vs and the voltage across the inductor is L di by dt plus voltage across the capacitor, as we have already taken it as V0, I am writing it as V0. And what I need dIL by dt. So keep this term here, move the remaining terms on the other side. So you will get this equation which I name it as equation number 1. Next step I need to get one more state equation or one more electrical equation. So one thing here is you cannot straight away apply you can apply another KVL equation also, but the thing is I need another equation in terms of Is as well, because I need to have the equations in terms of state variables and inputs, because x dot is equal to Ax plus Bu. U is inputs. Now to consider the current Is, so I can apply to a current equation, that is KCL, Kirchhoff's current law, to this node 1. So please note, as these two nodes are directly connected, so these together is treated as one node. Okay, now for this node I apply KCL. So KCL says incoming currents are equal to outgoing currents, or algebraic sum of currents at a node. Algebraic sum of input currents and the output currents is 0. So for this node, the IL is the input current, Is is the input current, and the current through the capacitor and the resistors are the outgoing currents. So they are written as negative. So the usual convention what we follow is incoming currents are positive and outgoing currents are negative. So here is the KCL equation. Now what I want an equation in terms of x dot, which is dV0 by dt. So keep this term Move this term on the RHS side and write the equation. Rearrange these terms. You will get this equation, which I name it as equation number 2. Now write the equation number 1 and 2 again and write them in matrix form. Now what you understand here is the first column, the first term here in x is IL. Therefore the first column are the coefficients of IL in the first equation and second equation. So in the first equation there is no IL term, so we have 0. In the second equation we have IL term whose coefficient is 1 by c. It is written here. Now the second variable is V0. So in the first equation the coefficient of V0 is minus 1 by L. The same thing is written here. In the second equation the coefficient of V0 is minus 1 by RC, so it is written here. This is how you write the equations or the matrix. So this is nothing but the coefficient of IL, and this column is coefficient of V0. Now plus B into U, where U is Vs and Is. So in the first equation the coefficient of Vs is in the first equation the coefficient of Vs is 1 by L. There is no Is term, so 0. This 0. In the first equation the coefficient of Vs is 1 by L and coefficient of Is is 0. So these two terms. In the second equation the coefficient of Vs is 0, coefficient of Is is 1 by c. So this completes the state equation. This is the complete state equation. So if you notice one more thing, in the circuit they had given the values of C, L and F. So we can substitute in this. So this is of the form x dot is equal to Ax plus Bu. Now we can substitute L equal to 1 Henry, C equal to 1 F and R equal to 4 in this equation. You will finally get the one boxed with the red here. The last equation is nothing but the state equation. Next step is simple. It is actually the output. As we consider V0 itself as Vc, so output Y is straight away V0. So V0 is nothing but, we can write the same thing in matrix form. The only term that you get is 1 here, which is the coefficient of V0. The remaining terms are 0. So this is of the form Y is equal to Cx plus Du, which is the output equation. The state equation and the output equation together will form the state model. So there are, in textbook there are a number of problems solved in this, and in the notes shared with you there is one more problem which is of the similar kind. So you can practice more and more problems to get perfect with this. Thank you.